Hello, hello, hello. All right, so we are moving into our our lesson in Unit 4, and this is on definite integrals. So this is actually learning what the definition of an integral is. We're finally up to that point. I got a little warm up here on Riemann sum using a chart. You're welcome to try it. We will probably do this for a warm up in class together, not a part of the video. Now here's what we're talking about, that definition of an integral. So this is that first official day on it. Now, I remember back in the day we learned the first and official definition of a derivative, and now we're doing it for an integral. So you have to be a little bit, you have to kind of picture this a little bit, and you have to kind of work with me on it a little bit, because the notation can be a little weird. It's a little bit more weird than that of a derivative, but let's just read through it. So this is the definition of a definite integral. So I keep talking about the word integral constantly and how it's the second part of calculus. There is two types that we talk about. This first one is the definite integral, and we'll discuss the difference between that and an indefinite integral later. But for now, just know we are talking about the definition of a definite integral. Okay, here's the criteria. If f is continuous and defined from a to b, all right, we divide a to b into n subintervals of equal width, which we call delta x, and that's b minus a over n. And if you think back to our last lesson, that is just telling us n is the number of rectangles. Okay. And that b minus a over n, that's just going to be the length or the base of each rectangle. Okay. So something else that we're going to do notation-wise is we're going to let x sub zero e our a value. So that first x value, that left value on our interval. And we're going to have x1, x2, all the way to xn, which is going to be our b value. These are going to be the endpoints, all right, of these subintervals. And the way we wrote that is it's going to be kind of like the heights of our rectangles. So this is kind of a review of yesterday's notes. Right? Now, for notation purposes, we're going to call those points, any point in between it, any points in the subintervals. Okay? We're going to be looking from the first, the second, the third, all the way to the nth point. Now, I don't want this next part to confuse you here, okay? But there are 4 different formulas written here, all of which are the definition of a definite integral. But they're written 4 different ways, okay? You got it written in terms of the right Riemann sum and the left Riemann sum and the midpoint Riemann sum, okay? They're all right, and they're all talking about a definite integral. The only difference is the heights of our rectangles, which you're seeing as I underlined there. Okay. Now they're all finding the same thing, but the one we're going to look at is just this first one. Okay. This is the first and only definition that we're going to look like, and it's pretty much the same as the right Riemann sum definition, but just notation-wise, this is how it's written. Okay, here we go. This box right here, what I'm circling right here. This is literally how you write the notation for a definite integral. Okay? You can't tell because of the typing. I'll write it right here. A definite integral from a to b looks like this. It's actually the symbol on the front of your textbook. It's like a little S-looking shape, and it goes from a to b. This is literally saying the area under the curve, or the definite integral, from a to b. It's finding that exact area. Okay? So that's the notation. So this is saying find the exact area underneath the curve of f of x. And the dx is just a fancy way of saying, how do I put this? The delta x. It's another way of saying delta x. And we'll talk more about that later. But this right here, this is the actual definition of a definite integral. It is the limit as n is approaching infinity, so an infinite amount of rectangles, and we're going to add up those infinite amount of rectangles on our interval. Okay? on our interval A to B. That's going to give us the exact area underneath the curve. So what I'd like to do is show you exactly where this kind of comes from. I'm going to kind of build up to it. So I'm going to show you how this formula is kind of created. We're going to start with a picture. And I'll start it off right here. I'll draw the picture right here. Okay, we'll kind of do that same kind of image we talked about on Riemann sum day. Okay. Let's say that we're looking for the area under the curve between A and B. Right? That's my endpoints. Right? Well, let's draw this as if we're doing maybe a right Riemann sum. Okay, so it kind of looks like this. Okay. So the idea is to have more rectangles than that, but let's just say that's what it looks like. Okay. Now remember notation-wise, I'm going to call that first A value x sub 0. Okay. And the next point I'm going to call x sub I. All right, x sub I. And I'm going to keep going all the way until I get to x sub n, which is my b value. And I just represents any term between 0 and n. So this could be I is 1, or I could be, I plus 1 is 2 or 3. The point is I represents any term between 0 and n. And this is purely for notation purposes. Okay? So let me kind of define I. X sub I is just equal to our first term x sub 0 plus, and it represents any x value in that interval A to B. So how we write that is the length of any of our rectangles, which is b minus a over n, times I. So for instance, if I want to know this x value right here, all right, that's x sub 0 plus, and that would be 2 for my I value, 2 of these lengths. So that would give me the second I value. I would plug 2 in for I. Okay, so it just tells me any of those x values. Another way to write that is x sub I equals x sub 0 is a, right? We said it's a. And we got b minus a over n. And I'm going to keep this as I. Okay, we're building up to this formula here. So let's keep going. Okay. Now remember how Riemann sum works. Okay, we're finding the area of those rectangles. I'll call that a subscript rectangle, maybe. And remember, that's just base times height. Right? It's base times height. Okay. Well, if I'm doing this area, remember that the base, how we write the base, is b minus a over n. That tells me the subinterval. It tells me the lengths of those bases. And remember that the heights are all the x values, okay, are all the x values plugged into the equation. So I'm going to say f of, and the notation I'm going to use is x sub height to represent all the x values. I kind of set that up here. All the x values on that interval. Okay. So remember how this works. Area. This is pretty much how Riemann sum was set up. It's b minus a over n, so the base, and then times all these heights. Well, what we did, if you remember from Riemann sum, is we added all of those heights up. Okay, we had more than one height. So how we represented that is we added up all of the heights from the first term to the nth term, especially if we're talking about right Riemann sum. Okay. And f of x sub I, which, remember how we wrote up above, x sub I is just a plus b minus a over n I. Okay. So area is base times height. Base is just the length of the subinterval divided by n. And then the height is just us adding up all those x values on the subinterval. Okay. Now, this right here, I know it may not look like it, but I'm trying to stress this as much as I can. This is Riemann sum. This is the notation for Riemann sum. This is taking your base, which we did yesterday, And then this represents all of the heights on the subinterval. I was just trying to build up to that using the notation. Okay, so that's Riemann sum. So if and this right here, this was just an approximation, right? This was just an approximation. If I wanted to know the exact area, remember how we kept improving the area was to keep adding more and more rectangles to keep making my n value larger and larger? Well, we discussed the idea of what if I had an infinite amount of rectangles on that interval? What if on that curve, here, let me draw that curve right here again. What if on that curve, I drew an infinite amount of rectangles? I mean, an infinite amount. So much so that eventually it just looks like the area underneath the curve. So what if I take the limit to infinity of all of that stuff? B minus A over N times the summation I equals 1 to N of f of A plus B minus A over N I. This right here is the definition of a definite integral. And the notation we use for that is the integral, that's the integral symbol, from A to B of f of x dx. Okay? F of x dx. All right. Let's look at some examples real quick. Now, this right here is not an exact area yet, but it's going to be pretty dang close because we're using 75 rectangles. Now, you can be my guest. We're looking between 2 to 3. You can be my guest and draw that out, draw 75 rectangles, and do 75 areas and add them together. But we have an easier way. Okay? If I want to do 75 rectangles, that's not a limit as n goes to infinity. We do have a formula. Okay? This is just approximating, so we're just going to do Riemann sum. And the formula is that without the limit, and that is b minus a over n summation I equals 1 to n of f of a plus b minus a over n I. Okay? This is base times height. All right? It's just adding up all those heights. 75 rectangles, this will do this for us. Okay? Now, if you were to graph x squared plus 3, looks something like this, and we're looking between 2 and 3, that's that area right there. Now, could you imagine drawing 75 rectangles? Can't do it. But would you agree that 75 rectangles is going to be a pretty dang close approximation? 75 is a lot. Well, let's plug in all the values. Okay, so 2 is our A value, 3 is our B value, 75 is our N value, and I believe that's all we're going to need. So let's see what we got. The approximation is going to be 3 minus 2 over 75, so B minus A over N. It's going to be the summation I equals 1 to N was 75. Okay. And then it's going to be f of, instead of a, it's 2. Instead of b minus a over n, it's 3 minus 2 over 75 I. Okay. And then we just solve it. We just solve it using our properties that we learned before. Okay. Now let's solve it. So 3 minus 2, that's 1 over 75. Summation I equals 1. Now, I went ahead and plugged in 75 for n because we are using 75 rectangles here. But let me give you a little trick. Let's keep that as n for now, and you're going to see why. So we got 2 plus 1 over 75. I'm sorry, not 75. Let's call that n, because you're going to see this going to simplify this down for us a little bit. So that's 1 over n I. And oops, you can see right here at the 75, I left that as 75. I'm trying to prove a point here. Okay? So just like don't plug in just yet because I promise you that you're going to see it's going to make our lives a little bit easier. Okay, if we don't. All right. So let's start off by figuring out what f of is. So this is just function composition, meaning we plug this into our equation. And remember, our equation was x squared plus 3. So let's see what happens when I do this. Okay. All right. So I got 1 over n, summation I equals 1 to n. Instead of this now, I'm going to go ahead and plug this in for x. So what I have is really 2 plus 1 over ni squared plus 3. So I just went ahead and plug that in. Okay, we're taking the summation of this. Now that we're to this point, does this look like anything we've seen before? Yeah, absolutely this should. This is day 1 of sigma. This is day 1 of sigma notation. We learned how to take this derivative. I'm sorry, this summation. So from these steps down, this is just what we learned day 1. So all we're going to do is simplify and solve using our properties here. Okay, so I got 1 over n. This is the summation. I equals 1 to n. Let's simplify this part out. If I were to FOIL this out, it would be 4 plus 4 over ni plus 1 over n squared I squared, and then plus 3. Okay? And it looks like the like terms that we can combine together are the 4 and the 3. So if you think back to day 1 of sigma, how we kept solving this is we expanded it and then we separated it. So this is what I'm going to do. I'm going to have 1 over n that's going to be multiplied by, and I'm going to separate all these summations. It's going to be the summation I equals 1 to n, and I'll go ahead and combine 4 and 3 together to 7, plus summation I equals 1 to n of 4 over ni plus the summation I equals 1 to n of 1 over n squared I squared. And then remember what we did after we separated this, and some of y'all have done this in the same step, but we can pull out the constants. Okay, everything but I. So then the last thing what I'm left with is 1 over n, and then I got, I got the 7 pulled out on the outside of this first summation. So I had the 7 pulled out. I got the summation I equals 1 to n of 1 now, plus I pulled the 4 over n out, and I got the summation I equals 1 to n of I, plus I got the 1 over n squared pulled out, and I got the summation I equals 1 to n of I squared. Okay. Now remember what we do from here. We have formulas for what these values equal. And this is why I told you to leave it as n, so you would make sure to recognize the formulas whenever we got down to this point. And then after we do this, you can go ahead and plug in what n equals. So what I got is 1 over n, 1 over n. This is 7 times. Remember that this identity becomes just n, plus, then I got 4 over n multiplied by, remember that this identity is the same thing as n times n plus 1 over 2, plus 1 over n squared. And remember that this identity was n times n plus 1 times 2n plus 1 all over 6. And now that you got rid of the summations, now we can plug 75 in for n. Now, my suggestion for that is to be extremely careful, okay, because it is a big problem. You want to make sure that you plug in everything correctly. If you want to try to simplify it down beforehand, by all means, go for it. But like maybe you can cross the ends out if you want. You could say the end crosses out with that one. You can try to simplify this as much as you want. You can take the 2 out. But whatever the case is, when you plug 75 back into that, be careful. When I plug 75 into that, I got that the area is approximately equal, because it still is an approximation, 9.367 units squared. Okay. Now, if you were to take the actual area underneath the curve with an infinite amount of rectangles, I guarantee it's going to be pretty dang close to that, because 75 rectangles between 2 and 3 is a heck of a lot. Okay? Now, I'm going to do one more video, or I'm sorry, one more lesson of doing something similar to this. Okay? Actually, yeah, I'm going to do one more video, or one more example like this. Because all we know right now is how to do it with a bunch of rectangles. I have not introduced the limit as n approaches infinity yet. So we're still just approximating. Okay, now once I say to find the actual area, we're going to include this piece right here, which again on day 1 of sigma we have learned how to do. This is saying no longer are we doing a bunch of rectangles, we're doing an infinite amount of rectangles. So then this would eventually become the exact area. Okay. But for now we're getting a really good approximation. And this is why I'm saying to leave n not as 60, but leave it just as n, because once we get to the actual limit part, you're going to see it's nothing different. Okay, we already know how to do that. All right, well, anyway, we're trying to find the exact area underneath the curve of 2x squared minus 1 between 1 and 4 using 60 rectangles. So it's still an approximation, but it's going to be pretty dang close. All right, remember the formula. B minus A over n is my length. And the heights of all these are the summations of I equals 1 to n. So that's to 60, but we'll plug that in at the end. And all the heights are going to be f of a plus b minus a over I. Okay? So let's plug in everything we know, but n. So b minus a, that's 4 minus 1, so that's 3 over n, multiplied by the summation, I equals 1 to n. And then that becomes f of a was 1, b minus a over n, we already said was 3 over n, I. And remember that f of x is equal to 2x squared minus 1. Okay? So we're going to simplify this out and do all the steps we learned in the sigma notation day. We're going to get a pretty good approximation of the area under the curve. Okay? So we got 3 over n multiplied by the summation I equals 1 to n, and we're going to start by figuring out what f of is, meaning we plug this in for x. So we have 2, 1, 3 over ni squared minus 1. Okay? And now we're going to, now that we get to this point, this becomes our lesson from day 1 of sigma. We're going to distribute, simplify, all that stuff. So I'll start by foiling that. So we got 3 over n multiplied by the summation, I equals 1 to n. Okay, this becomes 2 times 1 plus, okay, 6 over ni plus 9 over n squared, I squared minus 1. Okay. All right, last thing I'm going to do to distribute is multiply by 2, and I'm going to subtract 1. So I got 3 over n multiplied by the summation, I equals 1 to n. And then we're going to have, I'm going to go ahead and multiply by 2 and subtract 1. So 2 times 2 times 1 minus 1 is going to be just 1. And then plus 12n I plus 18 over n squared I squared. And I've already subtracted the 1. Okay? This is what we're left with. Okay. Now, for sake of time for this video, and sometimes y'all like to do this step, is I'm going to split these up. I'm going to split these 3 sums up, but I'm going to go ahead and take out the constants. I'm going to go ahead and take out the constants if that's okay. So what I have is 3 over n. Okay, I'm going to separate these summations as summation I equals 1 to n of 1 plus, I'm going to go ahead and take that 12 over n out. Okay, be left with I. And then plus, I'm going to go ahead and take the 18 over n squared out, and I'm left with the summation of I squared. Okay? Okay. And then from this point, hopefully you can see that I took the constants out, and then we have those identities left over, right? So what I can do is the identity for 1, I, and I squared. So I have 3 over n, the summation. I'm sorry, I don't have the summation anymore. I'm doing the identity. This identity becomes just n, plus I have 12 over n, and remember I is going to be n plus 1 over 2. And then for I squared, remember that it is n plus 1, 2n plus 1 all over 6. Okay, now that we got rid of the summation, remember that n equals 60. Now, this is the step that would change as soon as we would get to the actual exact area. From this point here, if I were to take the limit as n approaches infinity, I would just do my n behavior rules, and I'd have the exact area. But now, we're just approximating still, so we're plugging 60 in, just getting an approximation. So the area approximately equals, if you plug 60 into this very carefully, and maybe even simplifying down a few things if you really wanted to. You can say this is 3 and this is 1, whatever you want to. But very carefully, I got the area to be 39.7525 units squared. Okay. Now, I'm going to stop the lesson right there because we're almost at 3 minutes, or 30 minutes. But tomorrow, in class, we're actually going to do the exact definition of an interval, which we just learned at the beginning of the class, but the only difference is we're incorporating that limit as n approaches infinity. So this right here is just Riemann's sum. That's approximating it with very large rectangles, but now we're going to be incorporating that into infinity. And we're going to learn about B to A, all right, that integral, and learn all of its properties. Okay, that's it. Pick up where we left off tomorrow. Hope you guys have a fantastic